Okay, AP Physics, we are about to start chapter 27. To remind you what 26 was about, that was about what magnetic fields do to charged particles. They only affect moving charged particles, and basically it was like this. The force on a particle is F equals QVB times the sine of an angle, and you've got to use your right-hand rule to figure out which direction it points. Perpendicular to both the velocity and the magnetic field. And that was also equivalent to ILB sine theta. And my cheap proof that these are the same thing is that Q is in coulombs and V is in meters per second. Of course, these are Tesla. And this would be coulombs per second because that's what an ampere is times meters times Tesla. I think you can see that's the same thing. Coulombs times meters per second versus coulombs per second times meters, same thing. Units of B or Tesla, it's a Newton second per coulomb meter or a Newton per ampere meter. So anyway, we had established that, but that leaves open a question. Where do magnetic fields come from? Well, of course, they come from magnets, but where do they get the magnetic fields? And it's very suggestive here that, when magnetic fields act on moving charges, maybe, just maybe, moving charges make magnetic fields. They do, in fact. Using a current produces an electromagnet. So it's absolutely the case. You would have maybe suspected it anyway. But yeah, how much? In which way? In other words, what we need to do right now is we need to establish what the causal rule is. Like, in other words, if you have a moving charge, how much of a magnetic field does it make? What way does it point? Let's do the how much part first. And obviously, this is something that ideally is found experimentally. What we're going to do here, though, we're just going to conjure it up out of common sense because it makes lots of sense. First of all, okay, and again, we're talking about the source of a magnetic field. Like, where do you get them? And it's going to be moving charges. I would certainly think that a magnetic field ought to be proportional to the charge. If they're made by moving charges, hopefully the more charge you have, the more magnetic field you got. I mean, if I were making the universe, that's what I'd do. I would also make it proportional in some way to the speed. Now, the way the world is, sometimes the square of the speed, square root of the speed, there's lots of other things it might be. But hey, first guess, how about just the speed? Another thing that you would probably suspect based on prior experience, remember the gravitational field weakens with the square of the distance. So does the electrostatic field. It would be a little odd if the magnetic field didn't do the same thing. So I'm going to guess, because we live in three-dimensional space. Remember Gauss's law really explained in a way why we have an inverse square law? It's because when you have an influence radiate out from a point source into three-dimensional space, its influence covers the area of a sphere, and that area is proportional to the square of the radius. So it would make sense for this to be 1 over r squared. And just to kind of cap things off, there's angles involved here. Maybe there's some angle involved here. Now, angle between what and what we will establish with the directional stuff. This is a vector issue, But I will say it probably be proportional to the sine of some angle, the angle between what and what we'll say in a minute. You know what? You stick all this together, and B ought to be proportional to Q times V, probably times the sine of theta, over r squared, I guess. Again, I'm just conjuring this up, but it's right. But that brings up the issue of what's the proportionality constant. Now, you could figure the units of this constant fairly readily. You have to have Tesla on the left, and it's got to equal whatever the constant, I'm going to say just constant. I'm afraid to use a K because we've already used K for something. So equals constant times times coulombs times meters per second. Sine theta doesn't have any units. and this all gets divided by square meters. So the constant would have units of Tesla. Oh, hey, wait a second. It helps a little bit. Tesla meters. Seconds come up top. Yeah, the Tesla meter seconds per coulomb. What the heck? Well, it's a Tesla meter per ampere. God, what a weird constant. Of course, you could break down Tesla. You can break down Tesla. This is almost, it is worth doing. A Tesla is a Newton second per coulomb meter. So it's a Newton second per coulomb meter times a meter times the second over a coulomb. I hope I'm not making a mistake here. Good Lord. Is it a Newton second squared per coulomb squared? I guess. You know, I'm not even going to worry about it too much right now. But it's got to have a value, doesn't it? And you'd probably find it experimentally. You'd probably try moving some charge, measuring a magnetic field, seeing how much it is, and come up with the value. But we know the value. I know the value. I'll tell you what the value is. I'm just going to tell you. It turns out, well, the name of the constant, first of all, is mu naught over 4 pi. Raises the obvious question, why didn't you just call it mu naught instead of mu naught over 4 pi? Well, it's the same kind of story with the epsilon naught and the k. You know, k is equal to 1 over 4 pi epsilon naught and so forth. It kind of happened that way, that they wanted to do this for some reasons. But anyway, it's mu naught over 4 pi qv sine theta over r squared. Oh, but yeah, I mean, mu naught itself has to have a value. And I'll tell you what it is. It's 4 pi times 10 to the minus 7. I think it's a Newton per square ampere. I'm pretty sure of that. I'm so sure that I'm going to write it down. Besides, I think we actually had that going. Yeah. Weird. The value of the constant is precisely that. And that means that if I put it over 4 pi, it's just 10 to the minus 7, period. Not like 1.037 times that. No, it's just that. How did this happen? Historical stuff. Actually, it happened because of the way the ampere got defined. The way the ampere got defined was in terms of a couple of wires magnetically attracting each other. I'm not going to go through that again right now. I might bring it up later when we actually talk about parallel wires attracting each other. Then you'll see. But anyway, the constant is exactly, by definition, 4 pi times 10 to the minus 7 newtons per square ampere. So now that we've come up with that, what's the context? Like, where's the theta and what's the, do something with our hand again? Oh yeah, we're going to use our right hand again. So here's the deal. Now that we got down the bottom board, we got like what the relation is. Here's the context. If I have a charged particle, Q, I'll make it positive, moving at a speed, velocity, V, this way, I take my right hand again. And the way I like to do this, I can't remember if I learned this or not. Well, I probably made it up. I mean, who calls these bingers? You know, me, I do. Anyway, so these are your bingers again, just like they were before. Remember, we had bingers and your thumb and you pushed. Well, now the same anatomical parts here play similar roles, but in a different context. So these are still your bingers. They're still going to be the magnetic field. This is still your thumb. It's still the velocity. But what do? There's no palm pushing thing. Instead, let your hand curl around like this. This is your right hand. Try it now. Okay, like this. And then it's like your thumb points down the axis of these circles formed by your fingers. And in fact, the field consists of circles around this axis. So you take your thumb and it goes like that, and the field actually points out of the board up here. Now the strength weakens with distance, so you can make the things further apart. And it points into the board down here. And again, going weaker with distance, so I'll kind of spread them out a little bit. That's what it looks like. It also gets weaker if you're over here. That's where the sine theta comes in. The strongest field you're going to get is right when the particle's passing right by, partly because it's close. That's part of the reason, but also because of the perpendicularness of it. So the sine theta is this theta. So out here, at this arbitrary point out here, I've got an R. And, you know, you do the 1 over R squared thing, but you also have the, it's really just the component of how far it is from the axis. That's kind of what it amounts to. Did I say that? Yeah, now the theta is this. So that's the context. So it makes a magnetic field. I am going to go ahead and taunt's not the word, tantalize, that's the word. I'm going to tantalize you with an interesting result. We're going to try something really quick. This is partly an illustration of what this means. It's also to bring something up. What if I had a positive charge here moving at a speed v like that, it's charge q, just like that, and I had another one down here, also moving at a speed v. Okay, this is where it's going to get pretty interesting. This kind of excites me. In fact, I remember when I first had this epiphany that I'm about to mention. I can't call. I was in a dentist's office, but anyway, I'll kind of work my way back to that. Anyway, so they're separated by a distance r. So the first thing I'm going to do is I'm going to call them something. I'll call this q1 and this q2. Now they could be moving speeds v1 and v2. I'll probably make them the same, but for the moment I'll give them different names. So the force on 2 is equal to q, its own charge q2. It's a charge subject to a magnetic field. So q2 times its own speed v2 times the magnetic field due to number 1. Here's the way you think about it. This charge produces a magnetic field which influences this one. All right, so let's figure out what direction it points. I take my thumb and my fingers and it curls around. Of course, negative charge would make the opposite. But it curls around and causes a field into the board down here. Now this field again, I should have color-coded it, but I didn't. Oh well. This field here is due to this one up here. And then if you get your other rule, the one with the pushing with your palm, and figure out which way this one gets magnetically pushed, well, it's not hard. You get your fingers that point into the board, you get your thumb this way, it gets pushed up. Gets pushed up like that. There's a force. How strong of a force? This strong. But I think I'll go ahead and plug in what B due to that is. Now, of course, since I put them like right along, where theta is 90, I can just call that 1. And so it becomes F on 2 equals Q2 V2 and the B, mu naught over 4 pi Q1 V1 over R squared. I think I'll go ahead and make them the same charge and same speed, so I don't have to write all those things. So it really just becomes F equals mu naught over 4 pi Q squared V squared over R squared. That's easy. Probably worth your time sometime to confirm that gives you newtons. But in any case, that's the force we get. That's what this force is. Now, of course, what about the force? I mean, this one makes a magnetic field. What about the force on this? Now, if you do the same thing here, you're going to get basically the same answer, except the field due to, number 2, points out of the board. You come up here, you do your out of the board fingers and your this way thumb, and you get them again. Of course it gets pushed in. You knew it would, because Newton's third law, really. They got to be equal and opposite forces. So in other words, the prediction here is these two moving charges will magnetically attract. But it's two positive charges who electrically repel. Weird, huh? They are magnetically attracting, but they're electrically repelling. It's a love-hate relationship. Now, the question then becomes, which one wins? Well, now the electrical force between them, the electrostatic force is easy. It's K Q1, Q2, but I've decided to, for simplicity, make the charges the same. So KQ squared over R squared. The magnetic force, is equal to mu naught over 4 pi Q squared V squared over R squared. And I just set them, I didn't say why I was setting them equal. They don't have to be equal. Of course, they don't have to be equal. I'm setting them equal because I'm very interested in the condition that would cause them to fail to move apart. You see, electrically, they should repel and get further apart as they travel on. Look at that. Magnetically, they love each other and they're attracting, and so they come together. They can't do both. Somebody has to win. Or maybe they could tie. Let's make them tie. That's what I'm talking about. I'm talking about under what circumstances would the electrical repulsion be perfectly balanced by the magnetic attraction, so the two things, the two charged particles, move off in parallel with each other. So that condition's easy to calculate. Well, look, the R's cancel out. It doesn't even matter how far apart they are because both those effects are inverse squared. They're both proportional to each of the Q's, so that cancels out. I end up with getting that mu naught over 4 pi times V squared equals just K. So V would equal the square root of 4 pi K over mu naught. What's an expression? What's fun is to plug numbers into it. Let's do that. So if I plug the numbers in, the K is very, very close to 9 times 10 to the 9th. It's like 8.99 something times 10 to the 9th. It's got units. I won't write them right now. And this we just learned is 4 pi times 10 to the negative 7. But of course the 4 pi's are going to cancel out, and you're going to get the square root of 9 times 10 to the 9 divided by 10 to the negative 7, which means you're going to be taking the square root of 9 times 10 to the 16. Now, you folks are kind of okay at math in your head, I guess. Can you do that square root in your head? I hope so. Square root of 9, 3. Square root of 10 to the 16, 10 to the 8th. Does that ring any bells or cause any flashing lights in your head? Light bulb goes off? It's the speed of light. It turns out that for two charged particles to have as much magnetic attraction as they do electrical repulsion, they'd have to be moving at the speed of light, and then you would not see them move apart from each other. You wouldn't see them move apart from each other. One thing, 800-pound gorilla in the room, whatever you want to call it, motion's relative. You're the one, you, the observer, are the one who sees these two things moving. Do they see each other moving? No. There's no magnetic force between them according to them. The magnetic force only exists according to you, or observers who see them moving relative to them, the observer. So that's pretty weird. And you know what I'm getting at, don't you? Maybe. Relativity, special relativity. Einstein's 1905 paper was called On the Electrodynamics of Moving Bodies. And there's going to be a deep explanation for this weirdness that it just happens that the speed of light itself is the answer to this question. Now, I'll tell you what, I'm going to save that for another video because relativity really deserves its own video or videos. But in any case, so I'm going to erase this for now, and we're going to apply it a couple times. Obviously, that wasn't bad. You probably remember that. Of course, they put the equation sheet on there for you, but you know it anyway on the test, Okay, so what's a practical application? First of all, really, we don't very often shoot isolated charged particles across through the room. I mean, you can, but that's not the usual application. Usually it's a current, a little choo-choo train calling the line, while charges moving together. And the same thing we saw earlier, where QV was equal to IL. We'll check the units out. We just talked about it a few minutes ago with the effect thing. It's true for the cause thing too. If you want to figure out what magnetic field is, being produced by a wire carrying current, first imagine a little short chunk of wire. So short you don't really, from a distance it just looks like a point. So from out here, yeah, the magnetic field is going to be mu naught over 4 pi. Let's see, that's the constant. And then we got, I'm not going to say Q, V, I'm going to say IL over R squared. But you know what, this is pretty short. Since it's so short, I think I'm going to call it DL for the length. But that means it's just a little bit of field. So I've really got a differential expression, or infinitesimal little bit of the field is equal to that stuff. Oh, sine theta, got to be somewhere. We have here the makings of something called the Biot-Savart law. I'll go ahead and write that. Biot-Savart. I think it's two different people's names. The Biot-Savart law can be written either in this differential form like that, or it can be written as an integral. I'm a little more used to writing as an integral because in a practical sense, I want to know a current due to a field due to a big old long piece of wire, I guess. So in that sense, it becomes that you calculate B at a point in space due to some moving, currents, is mu naught over 4 pi times the integral, see I'm integrating both sides, of I dl sine theta over R squared. It's also, I'll tell you what, I'm going to recommend that you look in your book at some terminology. They talk about cross products. I'm using sine theta here and just assuming the direction is going to be taken care of with the right-hand rule, but really it's a cross product thing. Like when I wrote QV, probably should have written, QV cross R hat. It's a little vector notation for where you're at. I do need context here, though. I was talking about just a little segment, a little element of current. I might have a big long thing of wire. In fact, look, here's a long wire, and here's a point. Now I want to know the magnetic field at that point. Oh, what is it? Well, there's little DLs all over the place. I'll use this one for an example. Okay, there's a theta. There's an R. You do this and you add them all up. And you add them up all over the whole length of the thing. You can see that could get seriously ugly, seriously quickly, couldn't it? Especially if you have a crazy shape like that. Oh my God, that integral would be terrible to do. So what do? We pick our battles. We pick problems that we can do. And I'm going to show you a problem that was born to be solved by the Biot-Savart law. Here it is. The problem that was born to be solved by Biot-Savart. I wonder if you can guess what it is. I wish you were here so I could make you try to guess. Guess. All right, here it is. A circular loop. A circular loop of wire of radius r, and all I want to know is the magnetic field at the center. Can't get much easier than that. If the current is I, now do the Biot-Savart law. I'll really do it. It's B at that central point is equal to mu naught 4 pi integral I dl over R squared, integrated all the way around the whole thing. So beauty of this is you see that the R is constant because it's a circle and I'm at the center. So I guess I can just take the R and put it out here. And actually, I guess the I is constant. It's the same current throughout the whole loop. So it can come out front. Oh, that's getting better. Now I've just got to integrate DL all the way around from, I don't know how you want to say it, from here all. It's just too obvious. What's the sum of all the little lengths that make up the circumference of a circle? The answer is the circumference of a circle. So this thing right here is nothing more than just 2 pi r. So there's our expression, mu naught I times 2 pi r over 4 pi r squared. Out goes an r. Out goes that. The pi's go out. I get just mu naught I over 2r. That's it. Worth talking just a little bit about trying to make sense of it. Surely a bigger current, it ought to make more of a magnetic field. What about the R dependence? When R is bigger, the field is smaller. Like about twice the radius circle, the field's only half as much. But I thought it was supposed to be an inverse square law. Yeah, I'm twice as far when it's twice as big a circle. That makes a fourth as much, but there's twice as much circle. That partially undoes it, so I end up with an inverse first power law. Look, we just use Biot-Savart law. Your book uses it quite a bit. They do a thing where you do like, you got your loop and you got the field along the axis of the thing. And so I strongly invite you to look at that in the book where they do a slightly more sophisticated problem. But what I want to do now is try to use the Biot-Savart law to do another classic problem. And here it is. And it can work. Biot-Savart law is just true. It's the way the world works. So here we have a current. Here I have a point where I'd like to know the magnetic field. It's a nice, long, infinitely long straight wire, and this is R. And I want to know the field there. So I do Biot-Savart law. I think, well, could be worse, Could be that thing I drew the first time. It's not quite that bad. You could do the little, that's the R, and it's going to get squared. And yeah, there's a theta, and there's little bits of field that are going to point out at you here and into the board here. And you have to do mu naught over 4 pi times the integral. I guess, you know what? You could do this in terms of theta or x. If you want to do it in terms of x is going to be a variable like that, and you'll integrate from x equals negative infinity to x equals infinity. You'll have component issues going on, where you'll have maybe like a r over square root of x squared plus r squared thing, or one of those sorts of things. You can put it together. You can tell I'm going to weasel around this and not really do it very well. Your book does. Or I could do it all in terms of theta and integrate from theta equals, say, you could say negative pi over 2 to positive pi over 2. You could do that. And it's hard. It's one of those integrals that personally I, having not taken calculus recently, I still do my calculus, but I forget what's okay to forget. I might look it up in the Handbook of Chemistry and Physics, or if I had any sense at all, I'd do Wolfram Alpha or something. Or maybe I could figure out some little substitution use of, I don't know. I would do something, I guess, and integrate the thing. But frankly, it'd be kind of a pain. And in your book, it looks like a pain. It is a bit of a pain. They do it for you, and it can be done. But oh my gosh, it's really annoying. You know what it reminds me of? It reminds me of the situation with electrostatics, where we were trying to find the electric field here. It wasn't particularly easy until we came up with another way. Remember we introduced Gauss's law, where we ended up using some cylinder around the thing, some fancy geometric shape, and there was a holistic statement to be made, a generic holistic thing. Well, that's going to happen right now. I'm going to go ahead and say it, 28 minutes, but I can do it. It's called Ampere's law. There's this thing called Ampere's law, and it makes a generic holistic statement. Now, instead of using a potato, the internationally recognized potato is the shape to draw around an isolated charge, instead we take a trip. We do a contour integral is what it's called. You take a trip around the thing. If you got a lick of sense, you're going to take a trip that rides right along the field line. You're going to find a trip that's super symmetrical and keeps everything simple. Let me first write Gauss's law. It's like Gauss's law. It's not Gauss's law. So Ampere's law says integral of B dot dl, where L's a little bit of a trip, and this has got to be an integral where you go all the way around back to where you started. So some texts use this symbol there. It equals mu naught, there's that constant, I, the current. That's it. Let's do it. So I'm going to take a trip. If I got any sense, I'm going to take a trip with the circle with the radius r, so right along the field line. If I do that, then B is automatically parallel to my path at every point, and sine theta is 1. Well, it's the whole thing. Depends on how you we define our thetas. Anyway, so it's 1. So actually, this just becomes BL. And the L is, well, you integrate it, it's 2 pi r. It's the whole way around. So actually, I'm just going to say it. Well, I'll write it up here. Yikes. B equals mu naught I over 2 pi r. There it is. Now, that's terribly similar to what I wrote for that loop thing where we did use apsid, except for one thing, it's got a pi in the denominator. It's fun to think about. This is almost the same expression, but I'm going from being surrounded by a circle of wire to having an infinitely long wire. And I'm just as far from it. I've opened it up. You can ask yourself, should that make it stronger or weaker? You can have arguments on both sides. An argument for it making the field stronger would be it's longer. There's like a infinitely long piece of wire. Shouldn't that maybe make more field than just a circle? But wait, one problem is the really long wire, those pieces over here and over here, 2 problems. They're far away, and there's a square on that thing. So that ain't going to count very much. They're also in awkward directions where it doesn't add up. The components aren't doing a very good job. Actually, the more finite length of wire surrounding you, gotcha, from all different directions, is going to give you a bigger answer than this is. So it is weaker by a factor of pi. There you go. That answer can be gotten with the apsid law, but it's hard that way. So Ampere's law is easier. Ampere's law is also pretty easy to use for a solenoid, where you do the magnetic field at the center of this long thing like that. We'll probably talk more about that later. Solenoids are important things in physics, But I'm going to close with one more thing. Ampere's law is clearly analogous to Gauss's law. In fact, I might set up a little SAT, well, who do it anymore, but word analogy like this. It'd go like, Biot's law is to Ampere's law as Coulomb's law is to Gauss's law, where you've got the point-specific build it up, integrate from the ground up thing, for, say, Biot's or Coulomb's law. They're inverse square things, and imagine little point sources or tiny little bits. And then you have these holistic statements, like if you do the whole potato all over Gauss's law, you get 4 pi k q naught, but k q inside. And with Ampere's law, you take a trip. So very, very analogous. But wait a minute. What about Gauss's law itself? Does Gauss's law work for magnetism? What if you do draw a potato around some magnetic field lines? Does that tell you something? Actually, it does tell you something pretty interesting. If I have a magnetic field, for whatever reason, maybe it's because there's a magnet. That's a good way to make a magnetic field. Even if I make it out of moving charge, there's still these circles. So magnetic field, that might look like this, So what if I do draw a potato? That's my potato. Can you tell that field lines are sticking out and sticking in? In fact, there's just as many sticking in as there are sticking out, which means the answer is integral of B dot dA. And that looks just like Gauss's law over surface, just like Gauss's law, except that it's a B instead of an E. And the answer is 0. That's profound. That says that all field lines have to complete a loop and come back where they started. They have no origin and no end. They're closed loops. That is the nature of a magnetic field as far as we know. There's been a search for theoretical ideas about a magnetic monopole, like a North Pole. It's all by itself somewhere with field lines all sticking out. Nobody's ever found one. I'm not sure how that would work. People talked about it in the theoretical sense. But this says there are no magnetic monopoles. When you cut a magnet in half, it's like some of those lizards I hear about, like they grow a new tail, or I don't think the tail can grow a head, but they grow new ends. You break a magnet in half, The middle of it is just going to become a new south and north pole to go with the north and south pole and just have two separate magnets. And the field lines, they're like loops. And that's just the way they are. They have no beginning and no end. And that's Gauss's law for magnetism, which is one of Maxwell's equations. Going to learn more about that later. And here we are at 35 minutes. I'll shut up and I'll come back next time, say more about this and maybe about relativity.